What is up, multivariate gang? Today we will be talking about the cross product, another form of vector multiplication. Alright, oops, this is from an earlier take. Get rid of that. Alright, so, remember, I think it was a few videos ago when we were talking about the dot product. I told you guys to be very wary that you use a dot as opposed to some other multiplication symbol, because the other multiplication symbols mean different things for vectors than they did for scalars. The reason I said that is because we have our dot product, which is one form of multiplication that gives us a scalar, but there is another form of vector multiplication known as the cross product, which yields a vector. Alright, so how do we find the cross product? Well, it turns out the cross product is the determinant of a matrix. Yeah, sounds gross, I know. For the top row is the vector I hat, j hat, and k hat. And the second row is here. Hold on. We're going to be doing u cross v. Cool. All right. So u cross v is the determinant. Ux, ijk, ux, uy, uz, and vx, vy, vz. All right. So then we can break that down. This is why I said it's important that you guys learn ijk notation. So if we're going to go ahead and use this top row to break this 3 by 3 down. So if we go in that first cell and we just ignore the top row and the left column, we get uy, uz, vy, vz times I hat for that first part of the determinant. Oh my gosh. Then j hat, got to make sure we do minus, because it's remember the 3 by 3s, when you're breaking them down, you got to follow these rules. And hopefully you guys remember how to take determinants, because I'm not going to go over how to do those in this video. We get ux, uz, vx, and vz. J hat. Alright. And plus find coefficient of k hat. Ux, uy, vx, vy times k hat. Alright. And then we can, if we want a general formula, we can further expand that into the cross product equals uyvz minus uzvy times I hat minus uxvz minus uzvx j hat plus uxvy minus uyvx k hat. All right. Okay, let's go ahead and do an example. We've got vector u equals vector 1, 4, 7. And the vector v, which is 2, 0, negative 3. and we're looking for U cross V. All right. So that equals the determinant. Top row is I, J, K. Second row is 1, 4, 7. Third row is 2, 0, negative 3. That gives us, if we ignore that determinant right there is negative 12 minus 7 times 0, which is just negative 12 I hat. Minus negative 3 minus 14, so negative 17, so plus 17 j hat. And then 1 times 0 is just 0, minus 8 k hat. Beautiful. Looks really gross, but at the end of the day, it really isn't that hard. And you get pretty good at it as you go along. All right. Some properties of the cross product. U cross V equals negative V cross U, meaning they have the same length. They're just in different directions. Now, remember, you guys may or may not have talked about this in Algebra 2. So in a determinant, when you flip the rows of a determinant, you get the same number, except that it's negative. It's the opposite sign. Which is why if you flipped the positions of these two vectors, like if you switch them up here, then that's where you get the negative cross product. So this is to say that cross product is not commutative. Cool. All right, U cross V plus W equals U cross V plus U cross W. The cross product is distributive. It is in fact distributive. U plus V cross, whoops, that's supposed to be hold on. I did that one wrong. That's supposed to be U cross W equals U cross V plus W hold on. Let me look in your book. Okay, it's supposed to be U plus V cross W equals U cross W plus V cross W. All right, that's my bad, guys. Which is just another way of saying that that the cross product is distributive. Sorry, guys, that's my bad. All right. A scalar K times U cross V equals the scalar times U cross V, which is the same as U cross the scalar times V, which is another say that the cross product is commutative with a scalar multiplication, meaning that you can move a scalar anywhere throughout the cross product. Okay, and U cross 0 equals 0 cross U, which equals 0. If you cross the 0 vector with any vector, it yields the 0 vector, and U cross U, that equals 0. If you have in a determinant, if two of the rows are the exact same, the determinant is always 0, which is why that if you cross a vector with itself, it'll give you 0. All right. So there are some things that we automatically know about the direction of the cross product. So here we have U cross V equals that really long formula that I gave you guys. And we know that, and here's a proof that U dot U cross V is equal to 0. took the dot product, multiplied the components out, found like terms, and they all cancel each other out. The proof is in your book. You guys can verify if you want, and the exact same thing happens with v. So u dot u cross v and v dot u cross v, those are both 0. What does that mean? That means that u is perpendicular to u cross v, and that means that v is perpendicular to u cross v. The cross product is perpendicular to both vectors. Okay, so that means if you've got like a little axis right here, or not a little axis, you got these two head to tail, or tail to tail. You've got your guy can either point up and be perpendicular to both, or he can point down, be perpendicular to both. And those are the only ways that it can be perpendicular to both. And the way we know in which way it points is use what is called the right hand rule. All right, so in this scenario, we're crossing u with v. And how we'd figure out in what direction the cross product points is we would take our index finger and we would align it with our u vector, as I have not very artistically shown. We would take our middle finger or our palm and we would align it with our v vector, and our thumb points upwards or downwards, depending on how your vectors are oriented, towards the cross product. So if you ever forget, just use the right hand rule. It has to be a right hand. Does not work with your left hand. If you do it with your left hand, you'll get it wrong every single time. So that's the right hand rule. All right. Other properties of the cross product. So we know, let me just show you. All right, so you've got a vector u. You've got a vector v. We're actually gonna break out some parallelogram magic here. We're gonna break out the old vector addition parallelogram. Oh. All right. So what is the area of this parallelogram? Well, the area of that parallelogram, so first, here. What's the area of this triangle? Well, the area of that triangle right there is just the norm of u times the norm of v times the sine of this angle theta. And that's 1/2 all that. Yeah? That's a geometry theorem. And the area of this triangle is the exact same as the area of this triangle. So that means that the area of our parallelogram is just the norm of u times the norm of v times the sine of theta. All right, and so it turns out that the norm of the cross product, and I have to show this without true proof because I'm not a linear algebra master, is equal to that area of the parallelogram, which is equal to uv sine theta. Now, not to be confused with our dot product, which was uv cosine theta. This is uv sine theta. It's totally different. All right. So that is the length. Here, that's our direction. That is our length, and we get our direction from the right hand rule. And so u cross v, another thing to note, because of that little sine theta right there, we know that if u and v are parallel, that their cross product is equal to 0. Because if they're parallel, that means that the theta between them is 0. That means sine theta equals 0. That means the norm of the cross product equals 0, which means that their cross product is the 0 vector. Now, remember, if v is some, if u equals kv, if u is some scalar multiple of v, that means that they're parallel. So, if u equals kv, u cross v equals 0. The cross product of parallel vectors is 0. Cool. We will be furthering our exploration of the cross product in the next video. Goodbye.